Hi and welcome. We're going to go over this problem, rotated array, today with the empire method. So let's look at the problem description. So suppose a sorted array A is rotated at some pivots unknown to you beforehand. So that means 1, 2, 4, 5, 6, 7 might become 4, 5, 6, 7, 1, 2. So we just split the array at two between 2 and 4 and put 1, 2 in the back and 4, 5, 6, 7 in the front. So that's what it means to pivot the array of a sorted array. So find the minimum element. The array will not contain duplicates. So notes the use circular rotated property of array to solve the problem. Okay, so what we want to notice here is what the inputs and outputs are. So the inputs is a sorted array or a pivoted array. Pivoted array, pivoted sorted array. And the outputs is the minimum elements in an array. So let's look at some examples here just to make sure we understand what we're getting at. So if we have the array 7, 2, 4, 5, then the minimum element is 2, so we output 2. So if we have the array 3, 1, 2, the pivot array 3, 1, 2, then we output 1 since that's the minimum element. So that's all we have to do. So let's go about matching this problem to other problems. So this is similar to problems finding minimum element and also problems using binary search. Okay, so now let's plan this problem out. So the first thing that we want to do is to for exceptional case where array is size 1, just return one element in array. And then for the rest of the problem, we're going to apply binary search to figure out what the minimum element is. So we are just going to write apply binary search to find the minimum element. Okay, so let's just go about implementing this plan. So the first thing we need to do is take care of length equals 1. So we want to return the only element in the array. And then say we have, so we want to start our configuration for the binary search problem. So the binary search problem takes the endpoints 0 and length a minus 1 of the array, and it goes into a loop while L is less than or equal to R. Then we find the midpoints, which is L plus R divided by 2. And then if we find the elements, so then that element should be a m minus 1. So if m is the elements that the index in which the pivot is at, then am minus 1 is the only one. It's the only element that satisfies the condition that am minus 1 is greater than am. So we want to return A after it's found. So in all other cases, if AM is greater than or equal to A0, then we want to look at the right side of the array. So we want to split up the way. So this first step is basically if we split the array down the middle, and then if AM is greater than or equal to A0. So if we compare this element to the or if we compare this element to the first element, or let's do this 1, 3, 1, 2. So if we split it down the middle element is 1. And then if 1 compared to the first element is greater than or equal to, then we want to take the right hand side to find the pivot. And if it's less than or equal to, we want to take the left hand side to find the pivot. So else r equals n minus 1. And then we'll want to return A0 if it's not found. Okay, so we have a solution for this problem. This is a solution. So next we can review this problem. Okay, so let's go about stepping through this function. So we initialize the array A to 7, 8, 9, 0, 1, 2, 3, 4, 5, 6. And so first step is skip because the length is not 1. Then we set up the problem. We look at the endpoints, and the endpoints are in position. So to get the midpoint, so we get the midpoint, and then we see that the midpoint is not less than the point to the left. So we skip that, and then we see that the condition where the first element is less than or equal to the midpoint element is not true. So we skip down to Rn minus 1. So we look at the left half of the array, and then we keep on going, and we split again, and then we split again and search for the right or left half of the array, and then we find the middle element, which is 0, and we return the value. So now that we have a review of this problem, now we can evaluate this problem. So the evaluation of this problem is that it's O log n time complexity, since we're using a binary search to do this finding the middle element. And furthermore, this is O1 space complexity, since we're not using extra space to hold any elements or anything like that. We're just reusing the array. So we don't have any extra space that we're using. So this finishes the analysis of this problem. So thanks for watching.